So now that brings us back to depth first traversal, right? So like I said, we nuke this. And depth first traversal, depth first search goes deep before stopping and coming back. So for all the children of the current node, recursively visit the left children, then recursively visit the right children. And the question becomes, hold on, when do we check the current node? It's not here. We don't have anything about this. Well, it depends on which type of depth first search we're going to do. We actually have 3 different flavors of depth first search that we can run. So we can do pre-order depth first search. And pre-order depth first search, we check our current node before we visit any children, before we visit the left child, the right child, any of that stuff. So you can think of this in a binary tree as the first time you see an element. Or we can do in order, which is we check the current node after visiting the left, but before we visit the right children. So in a binary tree, that's the second time you see it. Or we can do post order, where we check it after we visit all the children. And this is sort of the third time you see it. So what does this mean for us? A, B, C, D, E, G, H. Okay. So if we do pre-order, we're gonna start at the root and we're gonna check before we see any of our children. So we go A, right, and we check that immediately. Then we look at our children. Well, we go B, right? We're gonna do our left, and we go to B, and we see it, and we go, okay, let's go to our left. We see D. Now we come back to B because we've done our left children, and we go, let's go to the right, and we check E immediately, right? And in each of these we go, well, we don't have any children here or here, so we don't really go anywhere, right? Okay, cool. So now we come back up the tree and we go back to A, and we've done our left children now. We've recursively done our left children. We've recursively done this. So we don't have to worry about this anymore. So now we can go to the right and we can say, cool, check our C. Now we'll go left children. Do we have any left children? We don't, so we don't do that. And we go to G, we go to the right. We look at that guy and then we go to H. And then that's it, right? No children there, come back up, go to the right, nothing there, come all the way back up. Okay. If we then go in order, we start at the root. Let me change my pen color. Right? We start at the root here, but we don't look at it yet, right? Because we've only seen it once. We do our root first, right? We go, okay, well, let's look at our left children. Okay, well, let's look at our left children. And the first thing we see, we get to D, we look at the left children. There's nothing here. So the first node we see is D. Then we come back up. Now we look at B. Now we go to the right. No children in E, no left children in E. So we look at E, right? Go to the right, nothing, okay? Now we come back up. Now we look at A. Notice how we started at A, we came down, right? Come down, come here, nothing. Look at D. D second. Come down here, look at E. Right? Second. Look at A. Come back up to A. The second time we see A, that's when we actually visit it. Now we go to the right. Okay. Go to the left, no children. So now we come back up to C and we see C. Now we go to the right. Okay. Does it have left children? Yes, it does. Go to left. H, does that have left children? No. Come back up, look at H. Does it have right? No. Come back up to G, look at G, go to the right, nothing there. And we're done. Okay. Finally, we can look at post order. And this is where we look at the node last. So we come all the way down, right? And we go D, then we come back to B. It's got a right child. We go to E, then we go to E. Now we're done with both. We come back and now we look at B, right? We come back up to B. This is the last time we see it. Come back up to A. Hey, it's got children on the right, so we go to C. Go to the left, nothing. Come back up. Go all the way down to G. It's got children. H. Okay, so now we go H, nothing. All right, nothing. And now we see H. Go up to G, where we go down, up, and we see G. We see C, and we see A. So depending on our traversal order, right, A could be first, it could be middle, or it could be seen last. Now, we have one more question. How does this work with non-binary trees? I'm sure you're asking yourself. And that's an excellent question. And the answer is this. It depends. It depends on your rules for what left and right are. So let's suppose that this was not a binary tree. Let's suppose that A had 4 children, and we'll say X and Y are in there as well. Well, we could partition left. We could say, hey, only the leftmost child is the left and everything else are the right children. Or we could say after the second child, or we could say, hey, after the third child, or we could say before the last child, everything before the very last one are the left nodes. It is implementation specific. So this is the tricky part. You can still do a depth first traversal on non-binary trees, but if this is the case, not only do you have to define whether you're doing pre, in, or post order, but you have to define what the left children and the right children mean. This is why we're only going to work on binary trees for this, because that gets complicated. So we can do our same analysis here, right? It's going to be more memory efficient than breadth first search, right? But if we go really wide, it's going to be slower for those kind of nodes. What are our uses? Well, we got all sorts of uses, but here's one great example. Mathematical notation. So how we traverse this tree is going to determine what format the equation is. Hey, and we've already seen a different format for this, right? This equation specifies, let me get my pen out. Traditionally, this is supposed to specify 3 plus 5 times 6 minus 2 times 2. Right? That's what this is supposed to show. And you can see that because if we grab this subtree, we get 3 plus 5. If we grab this subtree, we get 2 times 2. If we grab this subtree, we get 6 minus 2 times 2. Right? Well, if we do a prefix traversal, we will get what is prefix notation, right? We see this guy first, then we see this guy, then we see this and this, right? Then we come back up, come down this side, and we see this guy, then this guy, then this guy, then this guy, then this guy. These parentheses are added for your visual ease, but they don't have to be there, right? It could literally be times plus 3, 5 minus 6 times 2, 2. Similarly, if we do in order, we get infix notation, and look, we get our equation, nice and simple. And hey, if we do post order, we get our postfix notation. Isn't that snazzy? So just like we could use a stack to analyze this thing, we could use an actual tree structure and get our postfix notation simply by traversing this using a post order depth first search.